For this lesson, we're going to add a couple more tools to your triangle congruency toolbox. So we already have side, side, side. We're going to add two more. We're going to use two more tools: side, angle, side, and hypotenuse, leg, for explaining triangle congruence. So let's jump right in. The first tool is side, angle, side. It says if two triangles share two pairs of congruent sides, and a how about not and the pair of included angles are also congruent, then the entire triangles are congruent. So an important piece here is that we have two pairs of congruent sides and included angles. So we'll talk about included angles in just a minute. But what this means is that yesterday we had to show that we had three pairs of congruent sides for side, side, side. For side, angle, side, it says we only need two sides. If we can get two sides and one angle pair, then we can be a business. But this has to be the included angle pair. So that hopefully drives the question, well, what the heck is an included angle pair? So in our example here, it says find the included angle pairs. Included angles are angles that are in between the two sides that are given. So, or maybe better yet to say, is created by the two sides. So, for example, in this diagram, for segments GH, for GH and HI, the included angle is the angle that's formed by those two segments, namely this angle, or angle H, or maybe another way to describe the angle might be angle GHI. They're the same angle, just named two different ways. Similarly, for IG and HI, the included angle should be not angle I, because there's three angles there, but how about angle GIH, GIH. And lastly, between GJ and JI, either call it angle J, since there's only one angle here, or possibly angle about GJI. Again, the included angle is formed by the two sides. And it's very important that we choose this angle. You can't just pick any angle in your diagram. It's got to be specifically, if you're going to use this postulate, it's got to be the two sides and the angle between them, the included angle. Okay, so let's look at some examples of when we might be able to use this. Specifically, here's a classic one. So in this diagram, I'm given that AB is parallel to CD, and also AB is congruent to CD. I need to eventually prove that these two triangles, ABC, is congruent to triangle DCB. Okay, so like we did with side, side, side before, triangle proofs, I like proof maps for these. So again, I'm gonna start from the end and work my way backwards. So I know A, B, C, congruent to triangle DCB. And now I have two possibilities. I could use side, 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 or I currently also have side, angle, side. So now I'm going to have to do some analyzing. I'm going to try to decide which one of these two I'm going to try to prove it with, and then I can work through and try to find that information. So for example, maybe I'll try side, 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 because because I did that before, maybe I can try this method again. So I look at my diagram and I see, well, can I possibly get 3 pairs of sides that are congruent? Well, I have one that's given. We can certainly get this reflexive pair, that's 2. But I don't really see a good way to explain why AC is congruent to BD with information that's given. I don't know I can't just measure these like a ruler. I don't really know. I frankly just don't know anything about them. So that seems like it might not work. But I think the parallel lines the parallel lines here should help me find some angles that are congruent, because I know a lot about parallel lines. Specifically, I know that since this diagonal is drawn in, I know that it sure as heck looks like I have 2 parallel lines intersected by a transversal, which means that F patterns, so corresponding angles, are congruent, or sure as heck looks like I have a Z pattern, or alternate interior angles, specifically this angle here and this angle here. And note that sure it looks like I'm going to get a pair of sides, second pair of sides, and the angles that are formed between them. I can show all 3 of those things are congruent. So I certainly looks like I'm going to go a side, angle, side, and I just don't quite have enough information for side, side, side. But I think I can do this. So that means I'm going to do side, angle, side. And let's see if I can't explain why. See, 1 pair of sides is congruent. How about the pair that's given to me? How about AB is congruent to CD? Because that's given. Let's knock the other side pair out of the way, because that's going to be super short. It's just this reflexive side, so BC is congruent to BC. That's reflexive. So now the last thing is I need to explain why I have this angle pair is congruent. Well, I have parallel lines that's given to me, so how about I write that down? AB is parallel to CD. It's given. And then since they're parallel, I should know that some angles. So how about angle ABC going to angle BCD? Why is that? Why are they congruent? Because if lines are parallel, then alternate interior angles are congruent. That was the alternate interior angles again. Or you could just explain it. If the lines are parallel, then alternate interior angles are congruent. And now I have a side pair, and the angle that's in between them. With these 3 pieces of information, I can use side, angle, side to conclude the triangles are congruent. Okay? So let's write that out. We're given that AB is congruent to CD. And also that AB is parallel CD. Since AB is parallel to CD, then angle ABC is going to angle BCD because alternate interior angles are congruent when lines are parallel. finally, BC, congruent to BC by the reflexive property. Therefore, since we have two pairs of congruent sides and the included angle pair also congruent, triangle ABC is congruent to triangle BCB by side, angle, side. End of proof. It's a little bit more writing, but then again, there's a little more thinking. But note, I went through and I used the side, angle, side property. I worked my way through. I used the reflexive property, so that was taken care of there. And then finally, I claimed because of side, angle, side, the triangle is congruent. And I even marked it off on my diagram as I went through. This is a great example, a classic example of using side, angle, side. Let's now see an example of our other idea, which is called the hypotenuse leg congruence theorem. The hypotenuse leg theorem is very specific in that these two things are vocabulary words associated with right triangles. So it says for two right triangles. Very important. If the hypotenuse pair and a leg pair are congruent, then the triangles are congruent. Just as a refresher, for any right triangle, the side opposite or across from the hypotenuse, or from the right angle, is called the hypotenuse. And the other two sides, the sides that make up the right triangle, are called legs. So this theorem says that if you know that the two triangles are right triangles, and additionally you know one of the legs and the hypotenuse is congruent, then you can claim that the two triangles in whole are congruent. Okay? It's very important that this is for right triangles. This does not apply if the two triangles are not right triangles. So we've got to be pretty careful when using hypotenuse leg. Okay, so kind of like we did on the previous lesson, is there enough information to show two triangles are congruent? Let's state what the triangles are and what postulate you use, or postulate. So if we look at this, look at this diagram, say start with A here. Identify a couple triangles that look congruent. It looks to me like this guy and this guy. Or let's see, if I said triangle BAC. BAC is congruent to triangle, well, let's see, goes from 1 to 2 to back, so EDF. And why? They seem to have two pairs of congruent sides and an included angle. Looks like I could explain their congruence by side, angle, side. This diagram, let's see, I have a right triangle, so that's probably screaming hypotenuse leg, or at least I should consider it. I have two right triangles. I have the side opposite the right triangle, it's called the hypotenuse congruent. And can I find a third side? It looks like there's a reflexive shared side here. So I have hypotenuse, a leg, and right triangles. So absolutely, yes, I could. It looks like triangle, how about M and O? M to N to O. So 1 down to the right angle. So it looks like triangle R N O. Y by hypotenuse leg. Okay, so let's look at an example of a proof that you might use hypotenuse leg in. Or maybe we won't. Maybe we'll use something else. But let's, this one highly likely we'll be able to use it. So I have this crazy diagram here, and I'm told that JL is congruent to MK. JL is congruent to MK. Angle JKL is equal to MLK, and they're both 90 degrees. Prove why the two triangles are congruent. This example, so note that this picture is got a bunch of overlapping triangles. So what I'd like to do is I'm going to redraw this triangle. Before I do a proof or do anything else, I'm going to redraw these triangles. I'm going to draw out the ones I want to show congruent. So, for example, I'm going to take these and separate them out. And I know here's K, here's L, and here's J. And they might not be perfectly. Oh shoot, did backwards. Can't do this, that one. How about, and then K, L, M. And I know that this angle is a right angle, and that angle is a right angle. I also know that JL is congruent to MK. So what I'm really trying to show, not with this overlapping diagram, but I'm really trying to show that these two triangles are congruent. And can I do it? I think it can, because note that from the diagram, KL is shared. So it sure as heck looks like I could be able to show this. So let's see, from my little organizing map here, I have triangle JKL congruent to triangle MLK. I have now three possibilities. Side angle side, or hypotenuse leg. Looking at my information, let's see, I have right triangles that probably is screaming hypotenuse leg. Let's make sure. Do we actually have the hypotenuse? Yes, it looks like we have a hypotenuse are congruent. We have the leg is congruent, and the right triangles. Looks like this is the guy for us. I certainly can't show that I have two other sides. And the angle that I even have is not between them. So I'm going to have to go with hypotenuse leg. To show hypotenuse leg, I need to show that the hypotenuse is congruent, that the leg is congruent, and also that we have right angles. This is important. Or more specifically, right triangles. Right triangles, because recall that from the theorem, the hypothesis of the theorem says that for two right triangles. So we're going to use hypotenuse leg. We better explain why we have right triangles. And this is what gets people out. They kind of find this annoying. So let's pick a couple to show. I think the two legs are the easiest. Or the two sides. So hypotenuse, that's in fact just told to us. So I know that JL is congruent to MK as given. The leg, well, let's see, from the original diagram, that's a shared side. So KL is congruent to KL. That's reflexive. What's a little bit of a pain is this showing that they're right triangles. So I know I have some right angles. So I know what's given is a measure angle JKL equals measure angle MLK, which equals 90 degrees. That's given to me, but that's not enough to show they're right triangles. It's not right angles. So what I need to do in between is I got to claim that the triangles that I'm trying to prove not congruent, and MLK are right triangles. I got to show the claim that they're right triangles. Why are they right triangles? Well, they're right triangles because they have right angles. That's what our right triangle is. It has a right angle. Therefore, that's what a definition of right triangles. Since I have hypotenuse, since I have a leg pair congruent, and I have right triangles, that tells me that I can use hypotenuse leg to show that these guys are congruent. So my diagram is a little sloppy and well, frankly, a little bit on the confusing side. So I want to make sure that I write this thing out. So let's do that. So here we go. So proof. This is what we're given. So JL into MK. By the reflexive property, KLK is congruent to LK, or KL. Okay, so I'm working my way across. So now let's work the last strand here from top to bottom. Okay. Also, we're given that measure angle JKL equals measure angle MLK, which is 90 degrees. Because of this, triangle JKL and triangle MLK are right triangles. Therefore, triangle JKL is congruent to triangle MLK by the hypotenuse leg theorem. We got a little short here in comparison to the other theorems. You could have continued and written out in a little more detail here in the end, if you so chose. It's not the end of the world as long as your proof and your map are clear as to what you're heading out. This is acceptable. Adding some more to the conclusion here, maybe expressing maybe saying something to the effect of since you have a pair of since for these right triangles, the hypotenuse are congruent and a leg pair is congruent, then the triangle is congruent by hypotenuse leg. Could be a way to maybe spice it up, but this will do. And that is